Okay. And if you want to use the point one, the battery is set for the probably it needs replacement. This one. This one. This one is for last night. Yes, two. Yes.
Okay, welcome to the last talk of today, and I think we've conquered the technical problems. The floor is yours. Yes, but so I think we need to. Yeah.
That's time.
There's fun.
Yes.
This is not very.
No, this one is the auditorium. They are connected.
Okay.
This one is the big one, this one is the small
Okay.
No, you can see it.
Let's do science. Start the talk.
Okay, this title sounds a little bit informal. Okay, but this talk going to be a little bit informal in the sense that I just want to discuss some ideas and don't think it works.
Probably.
So this is my student slides. So this is based on unpublished and ongoing work with Santiago Rambiete, who is over there. Benefited also of discussions with Harvey Panta, Paul-André Méliès, Hugo Herbelin, maybe online, and also Joachim was visiting the Nico Institute a few months ago. Okay, so the outline of my talk, I will explain what I mean by textual mathematics. Actually, the words are mine. They are from that book that are shown by Ganesalingam. Then my goal is to speak about some phenomena that are related to the use of plurals, and to try to sketch the lines of the composition of semantics with that. And so I will speak a little bit about compositional semantics and just the framework in which I'm working. Then I will speak about plurals, and then I will look at the difference and the opposition between collective and distributive predicates, and show that this is quite important in math. And finally, I will speak a little bit about symmetric predicates, that is phrases that denote binary symmetric relations. So the textual mathematics, that's say the language that are used by professional mathematicians to convey mathematics. Typically, what you find in textbooks, in articles, and this is quite different from the complete formalization that you may have first order logic or set theory, or in proof assistance like Groote. consists of a mixture. There is a delay between the matter ici and what. It consists of a mixture of natural language and mathematical formulas, and it has its own structure, its own particularities, and that's why it is it's worth studying. So that image of that book, The Language of Mathematics, you saw it already on a slide, the presentation of Anne. And in that book, there is that quote by Anne saying that somehow the language of mathematics provides a kind of grammatical laboratory. Okay, and the point is not really that it is technically free from ambiguities. Okay, there are typically lexical ambiguities. For instance, if you speak about an ideal, if you are speaking about rings or about order theory, it's not exactly the same thing. Still, it's not by chance that they have the same, that when it's using the same word, it's not the same thing. But the point is that there is no discussion about what things are mean. So somehow one knows how solve those technical ambiguities. And actually, one doesn't even realize that there are ambiguities. Okay, so just let's take an example. This is an excerpt of Roger Godemont's Mot d'Algèbre, which is a book which is a little bit like a purpose for us because it has the advantage of being very well written. So it's good style mathematics. And this is a definition. Okay, I give you the English translation. Okay, these are actually two definitions that are on the same page. And definitions are very important in textual mathematics and in math in general. Okay, people sometimes speak about statements, about proofs. This is, of course, very important. But definitions are very important because they introduce new concepts. And if you think of a possible system that would interact with the user in a way close to natural language, okay? So if you think of something like a grammar, an underlying grammar, definitions, in fact, have that effect of augmenting the grammar. Okay, typically here, actually the typesetting, boldface and italic is from the book, okay? And so here, the definition introduces a new word, orthogonal. Okay, and on that same page, in the second definitions, you see that it also introduced the new notations. Okay, so you will have to augment your grammar with those notations and that new vocabulary. But then, if you look at that, okay, you're gonna see that what is defined is orthogonal with respect to f. But here, you have just orthogonal. But it's orthogonal with respect to f, okay? But with respect to f, and it's not repeated. But you have to retrieve it somehow. And another thing is that here, what has been defined, what you can infer as a rule is that you can say that two things are orthogonal. But here, not have that all vector x are such that for every vector y, x and y are orthogonal. Okay, you have orthogonal too, but that's the same one. Okay, so somehow you will have to enrich your grammar but also not just a simple context-free rule. You have to possibly infer possible use, possible linguistic use of that key word orthogonal that is introduced. Okay, now so this is just to present the setting in which I will try to formalize the things. Okay, and I take this sentence: a farmer feeds a grey donkey. I wish I had taken a man owns a cat, because the exam Reinhard took on the very first day. But what I'm using is a sort of abstract syntactic structure here. That's very close to what Reinhard was using. That's what he called semantic recipient. Okay, and this is a lambda. This is a lambda. This is indeed a type lambda term. So it's built on some signature, and that signature here is the following. Okay, so it says that farmer and donkey are nouns. That gray is an adjective or an adjectival phrase, but using a type, it means that it's a noun modifier. Okay, that feed is a transitive verb, so it takes two noun phrases, the object and the subject. The indefinite determiner, a farmer, a grey donkey, okay, is realized by that conjunction son, and it takes a noun and turn it into a noun phrase, and actually into a quantified noun phrase. Okay, and here I distinguish between simple noun phrase like John and quantified noun phrase like a farm. And I will be back to that at some point. And if I'm not back to that at some point, maybe implicitly you will understand what I'm doing. Which goes a little bit against Montague's traditions, where there is that idea of generalizing to the worst case. Okay. And then, of course, I cannot apply feed, which takes noun phrase, to quantify noun phrase. And so I have an operator, QR. And QR stands for quantification raising. Okay. And with that quantifier raising operator, actually, I could possibly manage to have another reading of this, which is not very interesting in this case, because I have two existential quantifiers, but that would model scope ambiguities. Okay, and once I have that, and this is where I differ a little bit from Reinhard with word. What I can do is just to give a sort of semantic interpretation, which is a sort of semantic functor, by interpreting each syntactic category as a semantic category, as a semantic type, in the tradition of Montague. So E and T are the type of entities, and T the type of propositions, so to speak, the type of truth values. So this is very close to the iota and omicron of church. And then I'm engaged also interpretations for my abstract syntactic construct. Okay, and this is functorial in the sense that it's consistent with types. Okay, so if I take the interpretation of the term farm, okay, it is a typed interpretation of the abstract type given to farm. And then simply this allows me to take my semantic recipe and interpret it in a complete decompositional way. Okay, so I will not comment all the reductions, but you see this is like compositional because technically that's a homomorphism. So the semantic interpretations enter all the components, and then I may unfold the lexical components with the definition that was given, and then just by unfolding and by beta reduction, normally I should reach a normal form, but I do not know why. I realized that I forgot the last beta reduction. I just saw that 5 minutes ago. But if I would perform that last beta reduction, finally I would obtain for a farmer feeds a gray donkey, that there is X a farmer, Y a donkey, that Y has a property of being gray, and then Y is fed by X. Okay, and so this is the things I want to use, but with plurals in this case. Okay, and there are several approaches to plural in the literature, at least 3 of them. I will not enter into the details, but one that one often encounter is based on mereology. So the idea is that you have an operator that allows you to build plural entities from singular entities. So you have atoms, and then you have an operations to combine those atoms. There is also an approach which is based on plural logic. And plural logic, that's a logic where you have actually 2 kinds of variables, singular variables and plural variables. And you have quantifications on singular variables and plural variables. Of course, there are some axioms, etc. And then something which is more into the tradition of Montaigne was just to use second order logic, okay, in the sense that a plural entity would be considered to be a set. Okay, and maybe it would be interesting, I think, to compare those different approaches from a technical point of view, really from a technical point of view. A lot of arguments, pro and cons, one approach with respect to another, are based not only on plurals but also on mass nouns. Okay, that gave puzzles in natural language, but we haven't found up to now mass nouns in math. Okay, and from a technical point of view, as a matter of fact, technically plural logic can be formalized in a fragment of second order logic. Of course, tenants of plural logic will say, yes, but plural logic is the good concepts. You are like implementing it in a sort of assembly language, but technically you can do it. There is a result by Tarski that they'd like to certify that shows that mereology, that's Boolean algebra without the 0 element, without the value. And then you also have Stone representation theorem that says that every Boolean algebra may be represented as a field of sets. Okay. So I think that just to stick that we are going to use sets, it's not that. That's what we are going to do. Okay, and so remember that I had noun, noun phrase, and quantified noun phrase in my example. and those were singular categories. So just by analogy, I'm going to have plural noun phrase and plural counterpart. And those are exactly the same, except that I'm replacing the entity by a set. And now, yes. Now the point is that you see, if I have something like a property and I'm working with that, okay, that of a gray donkey, want to see the gray donkeys, I must be able to apply such a predicate on a set. Okay, and this in the literature is called distributivity, but I mean, it's quite straightforward as a definition. Okay, you have here predicate, the property that applies to entity. S, it's a set, or if you prefer, the characteristic function of a set. And then you say that for every X in that set, you apply the property. But in fact, if you look at it, okay, it is type EROT, EROT, ROT. Okay, and to say that S is a set and that P is a property, that's purely arbitrary. Okay, so this is just inclusion. Okay, you may consider S and P as sets. This is just S is included in P. Okay, it's inclusion in the reverse order. Now, if you take P to be a set and you apply this to P, okay, you're going to have the set of sets S that are included in P. Okay, so this is just the power set. Okay, this applied to P is just taking the power set. Okay, so now let's try to. The farmer feeds some donkey. Okay. No, farmer, donkey, feed, some, QR, they are still the same, like in the previous slide. But since I need also a plural for some, I will also need a plural for the quantification raising indices. Okay, and so here what I have in addition is a plural operator that will be the translation, the semantic translation somehow of the syntactic plural marker. Okay, so it's gonna take the singular and turn it to plural. So donkey gonna be like donkey, but donkey is gonna be PL applied to donkey. And then I have that distributivity operator, okay, that turns somehow a predicate that applies on entities into a predicate that applies on sets. Semantically, that's what it does. Okay. But from a syntactic point of view, we may think of this as taking a verb phrase and turning that verb phrase into a plural verb. And so now my syntactic, abstract syntactic structure for a farmer feeds some donkey, well, it's almost the same as previously, except that that's the plural. Indefinite article, no, which is not syntactically applied, that apply to donkey, but plural donkey. And then I have to turn this predicate into a plural predicate, respecting the type here of the plural. this time I'm not giving you all the beta reductions. First, let me show you what are the semantic interpretations, logical interpretations of those new constructs. Actually, sum and the quantification raising operator, they are just the same. Okay, they are just the same. Is on type lambda. Is type lambda term, they do not have the same type. Okay, here X is of type EuroT, and those are predicates that apply set. And here same thing. This is like the identity, like F X, but no, X is a set. And F, no, actually it's a set. F is a set here. Okay, no, for the plural. Okay, I have those donkeys that correspond in my domain that correspond to singular donkeys. And now what is a donkey, a plural donkey? Well, that's a set of donkeys with at least two elements, otherwise it's not plural. And do not forget that the distributivity operator, that's the power set operator. This is just a set of all those p's that contains at least two individuals.
The type of P, the syntactic type.
Of PL?
Yes. Okay.
It's like that.
Would it be possible to just fold all the PLs and disters into some PL? Yeah, that was also it's
We could possibly make the generalized worst case strategy, and then have everything that occurs on set, and then among the power set distinguish the singleton that would be the atoms, and consider that those are the singular. But that's not what I follow here, and I think that I have more control with that. I hope I will convince you, or at least open the discussions. And so, after all the beta reductions, now I would obtain that there is a farmer X, and that there is a set S, which is a subset of the set of donkeys. That set is at least two elements. And each donkey that's at S is fed by the farmer X. Okay, that's what I want. Okay, no, there's something I think we may discuss about that, but there is something I think which is particular to mathematics. Okay, if I take this theorem, which is one of our favorite examples, we have been looking at that proof, etc. So that's theorems that shows that every finite vector space is a base. Okay, but look at the way this theorem is stated. Okay, you have X, which is a finite set of generators, plural. Okay, and then you suppose that subset A, the elements of which are linearly independent, plural as well. But actually, of course, this theorem is also valid for a line, for a one-dimension vector space. Okay, so and it will be used as such. So nobody nobody is claiming that this theorem just apply to vector space that are at least that have at least dimension 2. It's even the case that it works for in a completely degenerate way for the null vector space. Okay, because and in that case, the set A would be the empty set. Okay, and the set of generators, the base at the end would be the empty set. Okay. And so the conclusion of that is that I think that in math, for the plural operator, you may forget about this condition. But still, there is a difference of saying, for instance, that a set that contains just one vector is a set of linearly independent vectors. Why it does not make sense to say this vector is linearly independent. Okay. So this is maybe a first example of why I think it's good to keep a difference between singular and entities also at the level of types. Okay, now I want to speak about the difference between collective and distributed predicates. And a collective predicate, to make thing short, in this setting, that would be a predicate that apply on sets. Okay. But that do apply on set, but not taking a predicate that apply on elements and applying it to it the distributivity operator. Okay. And example in natural language, okay, are verbs like surround, the soldier surrounded before. Okay, if you take an explicit distributivity lexical mark like each, it does not make sense to say that the soldier surrounded before because each soldier surrounded. And the soldier were numerous does not mean that each soldier was numerous. And of course, if this distinction is quite important. And in the literature, there is a lot of discussion about ambiguities that come out of this. It's not clear that we have such ambiguities, or if we have, we know how to solve them. So, example of such things in maths is like the verb generate. By the way, those examples are real examples taken either from textbook or from a corpus that something. So clearly this does not mean that each element is generated. Okay. There is nothing like a co-prime number. Co-prime applied to a set of numbers. Interestingly enough, if you take the next example, which is an adjectival phrase, linearly independent, which is also a collective predicate. Every subset of a set of linearly independent vectors is a set of linearly independent vectors. This is not true for co-prime numbers. If you define a set of co-prime number to be a set such that the common divisor of that set is just 1, then 2, 4, 3, that's a set of co-prime number. But 2, 4, which is a subset of it, is not. But every superset of a set of co-prime number is a set of co-prime. Okay. So with respect to the sort of reasoning Reinhard was speaking about the first time, okay, the first day, and I guess that Larry will also speak of that sort of things. We have those kind of problems. And then there is also something a little bit tricky. Okay, that's the word, the noun generate. Okay, usually when you read about collective predicates, people say that typically that's adjectival phrase or verb phrase, but they do not speak of nouns, of common nouns having a collective flavor. And here in generate, you have like an overt collective predicate. Now, if we try to define prime and co-prime, give a definition of that in simply type theory, then it's not important, the very definition. What's important is that this is going to be of type EROT, applying on entities. But if you type it, this will be of type EROT, ROT. And now, with use distributed collective predicates, there is something which is that there are nouns that stands for collections or for groups. Okay, so if I take my my sort of military, then I can see the bataillon surrounded with fish. And then I may use this in a distributive way. Okay, and I can say like each bataillon is surrounded. But that's okay. That's okay. Okay. And of course, we have this in math. That's ubiquitous because we have sets. Okay, and so this is actually an example of the proof of favorite theorem. And so here it is enough to show that E generates M. In the statement of the proof, plus B with the element of which generate plural, but here singular. Okay. So there are let's do that. In the word "are," things like sets, dependent products are used to may vary the kind of elements you may have in the sets. There might be a sort of polymorphism. Here, I'm proposing something that still have behavior, which is to have a sort of reification. So to pass it in my object language, a relation, a binary relation, fact. And this will, so to speak, put together some entities, some individual corresponding to a set, with this characteristic function. And this is somehow what's happening in natural language. Okay. And then I may have predicates for natural numbers and rational numbers in my language, but also constants of type E that would correspond to that. And then I may give a meaning postulate, okay, that this constant it's in relation with this predicate, and this constant is in relation with this predicate. And then, of course, I need other axioms and meaning postulates. For instance, I certainly need a same set, let's say, a given set must have the same characteristic function. If I want the extensional, I need the other way around. Saying that two nouns for the same sets are equal. Okay, and this does not just allow to reify sets of entities, okay, because it may reify entities of that sort. So with this, if I want to try to formalize this, every set of natural numbers is a set of rational numbers. Okay, so at the abstract syntactic level, because I'm a little bit lazy considering natural number and rational number is Poisson expressions, okay, but it would be possible to have a compositional analysis of that. And then I have set of numbers. And this take a plural noun and I'm gonna turn it into a single. And then the abstract syntax of every set of natural number is a set of rational number. Okay, it's like this. Like this, and with the formula is defined identity. And now about the concerning the interpretation, okay, well, natural numbers, rational numbers, those are singular nouns. They should be interpreted as things of like EROT, so there's no, this is not surprising. For set of, okay, it takes the plural noun. This is a property of that. This is something of type EROT. And then it takes an entity X, okay, and a set of things like natural numbers, plural. Well, that's going to be the reification of a set S. This set S satisfying that property with an existential closure. And then this is finally what we obtain. Okay. For all X, which is a set, and whose characteristic function, which reify a set that is a subset of natural numbers, there exists a set Y that reifies a subset of the rational numbers, and X is Y. And actually, it's not very difficult from this to obtain that for all X, not X. And for this, you need what I did call the meaning postulate. You will need that. But with that, of course, the idea is that you're going to instantiate here S with a complete set of natural numbers. But for this, you need the postulate that says that there is an entity N whose characteristic function is snap. Okay, now, what about this one? And this is not true, actually. This is not true. But it's true only for sets that have at least two elements. The way I have defined co-prime, the empty set is not a set of co-prime numbers. It's a set of prime numbers, but it's not a coset. It's not a set of co-prime numbers. And singleton are not sets of co-prime numbers because singleton A may be divided by A. Okay. And but interestingly enough, in everyday language, where you say that the plural that's at least two, this is true. Okay, and so this time, okay, I'm considering that I'm in a setting where the numbers are the natural numbers. So number gonna be interpreted as the natural numbers, and prime and co-prime are just adjectives and intersective adjectives. And of course, the point is that co-prime apply on the plural. It applies. And that plural could be the empty set or a singleton, in which case it's false. But okay, and then what I have is my abstract structure, from which I will not be able at all to derive something like that. Every prime number is a co-prime number. Is this, and in fact, every spurious inference is blocked by the fact that okay, prime applies to number, and then I take the plural of it. But here, co-prime is to be applied to the plural of number. So there is a twist in the way the adjective and the plural mark.
Maybe you can use here the restrictor.
Pardon me?
Here you can use the restrictor.
What do you mean?
So for set of, you will but you need to introduce the restrictor of what I need to say that.
Yeah.
This is a restrictor is actually presupposition that it applies to at least two elements.
Yeah, but here I do not need any presuppositions. But by the way, there are a lot of presuppositions in that. In some example I gave, there were presuppositions.
But where does this
Yes?
switch come from linguistically? I mean, both of those look the same.
Yeah,
Why do you have this funny switch in there?
because
Only
of the,
because you need it.
because of the type of co-prime. But I would, it's like numerous. I would give the same type to numerous.
Because yes, now I see. Thank you.
Okay, now I'm turning to symmetric predicates, where there would be a lot of things to say. And it's well known that phrases, typically verb phrases or adjectival phrases that denote binary symmetric predicate may be used collectively. And so if you have that James agree with Carol, you can say James and Carol agree. And this is equivalent logically to Carol agree with James. Boston is quite different from New York. Boston and New York are quite different. Okay. Now in the literature, especially there is paper by Johan, where that sort of construction is the sort of constructions is discussed and showing that it's not completely regular. Okay, because if you say sue and then divorce, you cannot infer that sue divorced that, because it's maybe done took the initiative. Okay, and so there is a lot of things like that, but actually in math, symmetric predicates are symmetric, Okay, we do not have things like quasi-symmetric predicate. Okay, if a line is orthogonal, line A is orthogonal to line B, it's not line A which is over line B and that took the initial group or whatever. Okay. We do not have things like that. Of course, since mathematicians are jokers, I'm sure that if a good mathematician attends such a talk, he will invent some master in mathematics. Okay, and so symmetric predicates in math are symmetric. Okay, and now what I want to look, what I posit is that I have this key. Okay, if non-phrase one is adjective that denote a binary relation, then some preposition, and P2, so if A is orthogonal to B, then I can say that A and B are orthogonal. And now I should look at the different possibilities for my non-phrase 1 and 2. Okay, the non-phrase 1 should be singular, but nothing says that non-phrase 2 should be singular. Should they be simple, quantified, or something like that? Here are some examples out of our corpus. Okay, so the first one, simple case, d vector y, d vector x. Those are non-phrases, singular. Every row of hx, every row of hz, these are quantified, singular non-phrase. And here, for the second non-phrase, the first n eigenfunctions of the operator, this is true. So now I'm applying my scheme. And the vector y and the vector x are orthogonal, it's okay. Every row of hx and every row of hc are orthogonal. Okay, a lot of people will find it ill-formed or ambiguous or bad style. Possible reaction is to say every row of hx and every row of hc are orthogonal to what? Or the complete set like pairwise orthogonal or something like that. Okay, so that's not acceptable, and certainly not synonymous with that. Okay, and same thing. Same thing. So this means that my scheme only works with simple singular non-phrases. Okay. And so if I want to model this, I have to have an operator that takes two simple things and makes something which cannot be really a plural non-phrase. I must distinguish it from the plural. Okay, and so in fact, we have non-phrase that correspond to non-order pair. That's something that exists syntactically in some languages. Okay? That's the dual grammatical number, which I think exists in Britain, Russian. In Celtic languages, it exists. It also exists in classic Arabic, Persian, and Sanskrit. I do not know whether there is a relation between the fact that those languages have been used historically to write mathematics and the fact that binary relations are so important. Okay, so but that's I leave this for possible historian side. Okay, and then this corresponds to a pair, which may be defined like this. And by the way, in one of your papers about formalization of math, one of those papers in French you are using.
Yeah, no, I said. So it's not too many important.
So I'm almost done with my time. There would be a lot of other things to say. Okay. adjective denoting binary relation may also be used on collection with more than two letters. A, B, C, and D are part. This could be explained using sort of binary distributivity operators. Okay, for adjectives that are not that denote binary, the symmetric binary relation that is not transitive, or no, that is not replicable, then you need to remove the diagonal. Okay, this is sometimes done explicitly with words like plurals. Okay, so exactly like you have every and each that are distributivity, overt distributivity mark. You also have overt binary distributivity mark. And this is not far from reciprocal. So there will be a lot of things to say about that. But I leave that to Santiago for another possible talk. Just to conclude quickly, okay, I think that most of the semantic phenomena that appear in natural language also arise in textual mathematics. Okay. There are some that maybe do not, but like mass noun, I don't know. But somebody told me that there is no opaque context in math. That in math, everything is extension. You do not have any intention. Okay. And this is not true. If I say theorem x plus y equals y plus x, this is not the same as theorem x plus y equals x plus y. So just the word theorem is opaque statement. However, it seems that the use of another language in mathematics is much more regular. There's not all these exceptions that are discussed in the literature. For instance, we have distributive predicates, collective predicates. We have nothing like cumulative. Santiago found an example of something which is almost cumulative, but actually it is not, because the way it should be understood is clear from the formula. And then the main conclusion is that Arm was right. That's very interesting. And I also think that studying the linguistic structure of textual mathematics is also an interesting source of inspiration for the formalizations and conclusion.
I'm sure there are hundreds of questions.
All my questions are also
I have very many questions, but I just like to add an anecdote here. So there was discussion in this paper Journal of Pragmatics a few years ago about Gunnar Salingman's book, and someone was claiming that
the one with the half black sheep.
Sorry,
the one about the half of black sheep. The paper about pragmatics.
Yeah, the paper about pragmatics. The Journal of Pragmatics, and Gunnar Salingman writes somewhere that there is no pragmatics about in the language of mathematics. And then I don't remember what the background was, but they asked me to write a comment from the editors of the journal, and then I found that I actually looked at what pragmatics actually means. It means many different things, but then basically all of the aspects of pragmatics can also be found in the language of mathematics. So it's not only semantics, but also pragmatic phenomena. And actually, even in the examples of Gunnar Salingman, he just doesn't say that, or maybe he didn't know that they belong to pragmatic it's really a rich.
We had an example of that. It's not completely regular, but roughly speaking, binary relation, symmetric and transitive, you may apply it on collection with more than elements. If it is not, if it is transitive, it is of course reflexive because it's symmetric. So if it is not reflexive, then you have to remove the diagonal. So roughly speaking, you would say, okay, if it is not, if it is symmetric, but say not transitive, then you have to put pairwise. This is not as simple as that. It's not as simple as that. But then, if you take to be the opposite, that's a relation which is symmetric. Okay, it is not reflexive in general, and so according to what we would say, okay, let A be a set of pairwise opposite numbers, but you can only have two elements in that set. And so that's clearly for pragmatic reason that you are not trying to fool your reader by saying something like that.
Yeah. And the other example is, which you already mentioned, was presupposition, which is taken as some pragmatic. So it's mathematical text is full of those.
Yeah.
And even the example that you gave in the large cubes, when you put the threshold for large or for small, mathematical.
Yeah, Shashank, I think, was first. Let's see.
The question is about the coordinator and.
Yes.
So in this system, and does not take two singular nouns and produce a plural noun, right? It produces something of the category NP dual.
Yes.
I see. And then how does it interact with other predicates? Like if I say 2 and 3 are co-prime, is there a system to like, how does NP dual come in the whole picture?
Okay, so typically you would expect a binary, something which denotes the binary relations to be the ID was the following. The ID was the following. To have this is a lexical rule. Okay. Each time you have an adjective, you have an automatic lexical rule that would change the type of the adjective to be able to use it like that. But then to have such a lexical rule that is not over-generated, you need that.
Does dual a subtype?
Yes, I guess so.
You could also say
And it's not clear how the dual would work with the verifications.
because you can say also A and B and C are co-prime.
Yeah.
Even though the basic relation is the basic relation is plural. What was your example for the dual? It was, let's say, for equal, the basic relation is dual, but you can also say A and B and C are equal.
Yeah, so that's an equivalence relation.
Yes.
If you would say every row HX is parallel to every row HC, parallel would mean something. Okay, this would be acceptable both would be very bad stuff. I would not understand why you would not say something like all the rules of HX and HD are parallel or something like that.
Do you think that?
Especially if one is existential quantifier, the other one universal.
Not be quite
But do you think that actually your parsing and semantic rules could explain why they are unacceptable by generating too many interpretations? So let's say that these are syntactically okay, but then when you apply your rules, you will get too much ambiguity, and that explains why they are unacceptable.
The explanation
Yeah.
of the interpretation possibilities.
Okay, there is also something which my mind is not settled at all. Here I have been a little bit in a sort of Montegovian tradition, so a very poor type system. A very poor type system. Only entities and truth values. I think that a richer type system, where, for instance, you would not be obliged to use a predicate not, because you would have the numbers or something like that. That is also there is quite a space, an open space, a wide space for formalization.
So I was wondering how you conjoin singular and plural MPs like John and students.
Okay,
N1, N2 to NN.
yeah. So as I said, this is like informal and ongoing work, but it's well known. It's well known that
I'm not intending
It's
to
well
give
known
you a
that-
counterexample, just
conjunction. There are a lot of puzzles related to conjunction.
so you want to add another and
You could, yeah, you could imagine that you would have
I can
something
the
PSG,
example with distribute
PL,
coordination,
yeah.
coordinate structures.
Something like that.
So Montague he'll derive two conjoined conjunction, but in more sophisticated type theory, even simple one may have coordination or joint when run together, kiss each other. So then there will be the combination according to my coordination.
yeah, I know how. That is great.
Besides, there is an example of how we do too.
Yeah.
But one still will have distributed when each one kiss the other, but there are predicates where it is collective, like the soldiers. They'll do together something.
For collective predicate.
Yes. Because for some predicates one conclude will derive that each one of them did whatever they did. Well, we can say that each soldier surrounded the castle.
More questions? I think we would have needed a happy hour today to field the remaining questions.
But we can make it, I think, the bread and the cheese upstairs. Have bread and cheese in the kitchen.
Okay.
So why?
There is one. I cleaned some bottles inside of them.
Okay.
But they'll keep the bread till Friday. The bread will get
So,
morning.
okay, let's thank you all tomorrow morning.
For example,
about internal and external. So internal is you introduce mathematical like small.
C'est bon.
The external is well when
Yeah, I don't know.
so like say that every row